Hi there. Today we're talking about characteristics of the rational function. The rational parent function, your most basic rational, is y equals 1 divided by x. So if I was going to fill in this table here, I'd plug in the x and I'd end up with negative 1 over 9, negative 1 over 4, negative 1 over 2, negative 1, negative 2, negative 4. Of course, 1 divided by 0 is undefined, and undefined. Plug in a 1/4. 1 divided by 1/4 is 4. 1 divided by 1/2 is 2. 1 divided by 1 is 1. 1 divided by 2 is 1/2. 1 divided by 4 is 1/4. And then 1 divided by 9 is 1/9. So if I was to graph the rational parent function, if I just plotted these points, if I go negative 4, negative 1/4, negative 2, negative 1/2, and so on. What's going on here is this function approaches the y-axis and the x-axis, but it never touches it. We call that asymptotic behavior. Same thing's going on over here, I should say. If I plot those points I just found, I see some more asymptotic behavior. This thing approaches the x and y axes, but they never quite touch it. In fact, this thing has what's called an asymptote at x equals 0 and y equals 0. We usually represent those asymptotes with dashed lines. So the horizontal asymptote here is at y equals 0. And the vertical asymptote is at x equals 0. Those are the two imaginary lines that this function will always approach but never ever touch. That's the definition of asymptotic behavior. Approaches but does not touch. The intersection of those asymptotes is at the origin, 0, 0. So the domain is all real numbers except for right there at x equals 0. It's all of the x's except for the 0. And the way we usually write that is we say x is a number such that x cannot equal 0 and x is a real number. So let me break this down for you in plain English. This says x is a number such that x cannot equal 0 and x is a real number. That E thing right there says x is an element of the real numbers. It's just kind of like a C with a little line going through it. And the range is the same way. Y is a number such that y cannot equal 0 and y is an element of all the real numbers. The y-intercept is where this thing crosses the y-axis, and I just spent a lot of time telling you that this thing will never touch the y-axis, so there's no y-intercept. There's no x-intercept. The maximum, well, this thing's going up forever and down forever. There's no maximum or minimum. Okay? So, if we were to look at some transformations, underneath the fraction, that's going to shift it left and right. Outside the fraction, that's going to be up and down. So right here, this x plus 3, remember, next to the x is counterintuitive, so this thing's going left 3 and down 6. So imagine that the asymptote for the parent function is at 0, 0. If I go left 3 and down 6, that's going to move the asymptotes to right here. This is where they intersect. So I'm going to have an asymptote at x equals negative 3 and y equals negative 6. So let me just fill in that information really quick. Asymptotes, x equals negative 3, y equals negative 6. And of course, the x equals negative 3, that's your vertical asymptote, and y equals negative 6, that's your horizontal asymptote. So the domain is x is a number such that x cannot equal negative 3 and x is a real number. And y is a number such that y cannot equal -6, because it can't be the asymptote, and y is a real number. Okay, let's do another transformation. Let's do this next one here. This one says 1 over x minus 1 plus 2. So that x minus 1 means it goes right 1, and plus 2 means up 2. The asymptotes then go back to the parent function. If you go right 1 and up 2, that means this, where they intersect, is going to be right here, which means I'm going to have x equals 1 and y equals 2. So let's copy that down. X equals 1, y equals 2. This is the vertical asymptote. This is the horizontal asymptote. Now, with the domain and range, you're normally just going to see it written like this. X can't equal 1. The range, y can't equal 2. That's kind of how we shorthand the domain and range. And let's say that this is technically correct, but this is acceptable. You can write it both ways. This is probably the way you're going to see it more frequently. Let's do one more of these. Vertical stretch of 3. Left 1, up 4. So the asymptotes are going to be x equals -1, y equals +4. So x can't equal -1, y can't equal +4. And that's it. Let's try graphing some of these. Like this one right here. 1 over x minus 3 plus 1. So it's been shifted right 3 and up 1, which means the asymptotes are at x equals 3, y equals 1. Domain, x can equal 3, y can equal 1. I always start by graphing the asymptotes. So x equals 3, I'm going to put that with a dashed line. Y equals 1, I'm going to put that with a dashed line. From that intersection, you go up 1, right 1, and from the intersection you go down 1, left 1. We want to draw a curve that bends towards the asymptote but never touches it. Same thing over here, a curve that bends towards the asymptote but never touches it. That's all you've got to do. Let's look at one that's got reflection. See, we've got a -1. Let's do this one. Negative time over x minus 1 plus 4. That means it's a reflection. It goes right 1 and up 4. Which means my asymptotes are at x equals 1, y equals 4. X can't equal 1, y can't equal 4. So I would start with the asymptotes, x equals 1 and y equals 4. Now here, since it's a reflection, instead of going up 1, right 1, we're going to go up 1, left 1. It's a reflection. And down 1, right 1. So instead of being in quadrants 1 and 3, the effect of the reflection is that it goes in quadrants 2 and 4, like this. And that's how you do that. The last thing we need to talk about is how to find discontinuities inside of a rational function. Now, discontinuity occurs when the denominator is equal to 0. So a rational function will have a discontinuity whenever the function is undefined, i.e. at every value of x that makes the denominator equal to 0. If the factor cancels out of the denominator, there's going to be a hole. So if you can cancel something, there's a hole. If the factor does not cancel out, there will be a vertical asymptote. vertical asymptote at the 0. So for instance here, you can't cancel anything out, but look at the bottom here. You set that equal to 0. Something's going on. There's a discontinuity at x equals -2. And since it wasn't canceled out, we know it's a vertical asymptote at x equals -2. And since we didn't cancel anything, there aren't any holes. This next one looks like we can cancel out the x plus 4. When you cancel it out, there's just a 1 on the bottom now. So there don't appear to be any vertical asymptotes because there's no factors on the bottom, but there is a hole at x equals -4, the thing we canceled out. This last one here. Sometimes you got to simplify it. You got to factor it a little bit in order to be able to do it. And the way you do that, you can factor out the greatest common factor here of 3. Make this 3 times x minus 5. And then you can factor the bottom here, 2x squared minus 9x minus 5. Well, that factors to x minus 5 times 2x plus 1. So we can cancel out these x minus 5s, which means there's a hole at x equals 5. But there's still something left in the denominator, this 2x plus 1. We set that equal to 0. Subtract the 1, divide by 2. That means there's a vertical asymptote at x equals -1 over 2. So big picture here, cancel something out, you've got a hole. If you got a factor left in the denominator, you've got a vertical asymptote. And that's it for today. Thanks for watching.